Millman'S theorem. When a number of voltage sources are in parallel, having internal resistances R1, R2 up to Rn respectively can be replaced by a single equivalent voltage source V in series with an equivalent series resistance R. We have a network having the voltages V1, V2 up to Vn connected to the load RL and the resistances R1, R2, Rn. This can be replaced with a single voltage and single resistance. We need to find out these values. Then, since this is a parallel circuit, we can apply KCL. Then, at the load node, the currents I1 plus I2 plus I3 and so on up to In. Since it is a parallel network, we'll consider the conductance, that is G1 plus G2 and so on up to Gn equals to G, the current I. The voltage V is equals to the total current I flowing through this divided by the conductance G. I is I1 plus I2 and so on In divided by G1 plus G2 plus G3 and so on Gn. Then V equals to this. Let this be I1 V1 divided by G1. G1 is 1 by R1. Now current I1 equals to V1 divided by R1 plus V2 divided by R2 plus and so on Vn divided by Rn divided by G1 plus G2 plus G3. Everything is equals to equivalent conductance. V equals to V1 G1 plus or minus V2 G2 and so on Vn Gn divided by G. G is the total conductance of the parallel network and V is this, from which R equals to 1 by G. Step 1. We need to find out the individual conductances, that is G1, G2 and so on up to Gn by removing load. This is step 2, finding Millman's voltage by using this formula. Step 3, finding Millman's resistance. This R equals to 1 by G. Now, once you transfer this parallel circuit into Millman's circuit, you can find out the current I flowing through this by the formula I equals to V by R plus RL, where R is the Millman's resistance and RL is the load resistance. This is step 4.